Slip is the small difference between the speed of the rotating magnetic field, called synchronous speed NS, and the actual speed of the motor's rotor NR. Think of a treadmill that moves forward at a constant speed. A runner on the treadmill must run a little slower than the belt to stay in one place relative to the ground. That difference is slip. Mathematically, slip S is defined as S equals NS minus NR divided by NS. If the rotor turns exactly at synchronous speed, slip is zero and no torque is produced. In a real induction motor, the rotor always lags a little, so slip is a positive number, typically expressed as a fraction, for example 0.03 or a percentage 3%. The synchronous speed depends only on the supply frequency F and the number of pole pairs P. NS equals 120 F divided by number of poles. The rotor speed is what the shaft actually rotates. Therefore, slip tells us how far the rotor is behind the magnetic wave that is trying to pull it. The slip calculation formula is S equals NS minus NR over NS. Example, a 4-pole induction motor is fed from a 60 Hz supply. First find NS. NS equals 120 times 60 divided by 4 equals 1800 revolutions per minute. Suppose a tachometer measures the rotor speed, as NR equals 1725 revolutions per minute. Then S equals 1800 minus 1725 over 1800 equals 75 over 1800 equals 0.0417, or 4.17%. This means the rotor is lagging the rotating field by about 4% of the synchronous speed. If the motor were a 2-pole motor on the same 60 Hz source, NS would be 3,600 revolutions per minute, and the same rotor speed of 1,725 revolutions per minute would give a much larger slip of 3,600 minus 1,725 over 3,600 equals 0.522, meaning the motor would be far from its normal operating region and would not develop useful torque. Torque in an induction motor is produced by the interaction of the stator rotating magnetic field and the currents induced in the rotor bars. Imagine a child, the magnetic field, pulling a rope attached to a toy car, the rotor. The pull force times the radius, distance from the center, gives torque. The fundamental torque equation for a 3-phase induction motor, per phase equivalent circuit, is T equals 3 times V squared times RR over S, divided by omega S times open bracket open parenthesis RR over S close parenthesis squared plus open parenthesis X sub S plus X sub R close parenthesis squared close bracket. Where V is the phase voltage, RR is the rotor resistance referred to stator, X sub S and X sub R are the stator and rotor leakage reactances. Omega S equals 2 times pi times F is the synchronous angular frequency, and S is slip. The numerator shows that torque is proportional to the rotor resistance divided by slip, RR over S. That is, as slip increases, larger difference between NS and NR, the induced rotor current grows, producing more torque up to a point. The denominator contains the total impedance seen by the induced current. Higher reactance limits torque. This equation explains why torque rises with slip peaks, then falls. Maximum or breakdown torque occurs at the slip, where the derivative dt over ds equals 0. Starting from the torque formula T equals K times S divided by RR over S squared plus X total squared, where K equals 3V squared over omega S and is a constant, set the derivative equal to 0 and solve for S. The result is S max equals RR divided by the square root of X total squared. The corresponding maximum torque is T max equals K divided by 2RR multiplied by the square root of X total squared plus RR squared. Step-by-step example. Assume a 3-phase motor with V equals 230 volts phase, F equals 50 Hz, RR equals 0.5 ohms referred, XS equals 0.8 ohms, XR equals 0.8 ohms, so X total equals XS plus XR equals 1.6 ohms. Compute omega S equals 2 pi times 50 equals 314 radians per second. K equals 3 times 230 squared divided by 314 approximately 504. S max equals 0.5 divided by the square root of 1.6 squared equals 0.5 divided by 1.6 equals 0.3125, which is 31.25%. Tmax equals 504 divided by 2 times 0.5 times the square root of 1.6 squared plus 0.5 squared equals 504 divided by 1 times the square root of 2.56 plus 0.25 equals 504 times the square root of 2.81 approximately 504 times 1.677 equals 845 Newton meters. Thus the motor can develop about 845 Newton meters at a slip of 31%, after which torque declines. The torque slip curve is a graph of torque y-axis versus slip x-axis. It has 4 recognizable zones. Starting zone slip approximately 1, the rotor is stationary, slip is nearly 100%. Torque is low but rises sharply as slip falls from 1 to about 0.2 to 0.3. Pull-up zone slip between 0.2 and 0.05. Torque climbs quickly to its maximum breakdown torque. This region is where the motor can overcome the load inertia and reach speed. Rated zone slip approximately 0.02 to 0.05. The motor runs at its design speed. Torque is approximately the rated torque and varies little with slip, giving stable operation. Slip-induced loss zone slip less than 0.02. Slip is very small. Torque falls off and the motor becomes inefficient because the induced rotor currents and thus copper losses are tiny while core losses remain. By looking at the curve, engineers can ensure that the motor's operating point, load torque, lies on the flat part of the curve, not near the peak which could cause instability, or near zero slip which would give poor starting capability. Rotor resistance, RR, directly influences both the slip at which maximum torque occurs and the shape of the torque slip curve. A higher RR shifts the peak torque to a larger slip. Smax equals RR divided by the square root of X total squared, and reduces the peak torque value because Tmax is proportional to 1 over RR. In practical terms, a wound rotor motor lets us add external resistors in series with the rotor circuit. Adding resistance raises RR, which raises Smax and therefore provides higher starting torque. The motor can start a heavier load, while also limiting the starting current because the induced current IR equals V divided by the square root of RR over S squared plus X total squared becomes smaller as RR grows. Once the motor reaches near rated speed, the external resistors are shorted out or removed to restore low RR for higher efficiency and higher rated torque. This technique is widely used in cranes and elevators where high starting torque is needed, but running efficiency must be retained. Starting torque T-start is the torque when the motor is at standstill, S equals 1. Using the torque formula with S equals 1, T-start equals 3 times V squared times RR divided by omega S times the sum of RR squared and X total squared. Example, use the same motor data as before, V equals 230 volts, F equals 50 Hertz, RR equals 0.5 ohms, X total equals 1.6 ohms. Omega S equals 314 radians per second, K equals 504 as previously. T start equals K times RR divided by the sum of RR squared and X total squared, which is 504 times 0.5 divided by 0.25 plus 2.56, equals 252 divided by 2.81, approximately 89.7 Newton meters. Starting current I start per phase can be approximated by I start equals V divided by the square root of RR squared plus X total squared, which is 230 divided by the square root of 0.25 plus 2.56, equals 230 divided by 1.68, approximately 137 amperes. If we add an external 0.5 ohm resistor, total RR becomes 1.0 ohm, then T-start becomes 504 times 1.0 divided by 1.0 squared plus 2.56, equals 504 divided by 3.56, approximately 141 Newton meters higher torque, and I start falls to 230 divided by the square root of 1 plus 2.56, equals 230 divided by 1.89, approximately 122 amperes lower current. This illustrates how rotor resistance tailoring helps obtain the desired starting performance. A 4-pole 60 Hz induction motor runs at 1,740 revolutions per minute. Computed slip. Synchronous speed NS equals 120 times 60 divided by 4, which is 1,800 revolutions per minute. Slip S equals open parenthesis 1800 minus 1740 close parenthesis divided by 1800, which equals 0.0333 or 3.33%. Derive the torque expression T equals open parenthesis 3 times V squared times R sub R divided by S close parenthesis divided by omega sub S times open bracket open parenthesis R sub R divided by S close parenthesis squared plus open parenthesis X sub S plus X sub R close parenthesis squared close bracket, and identify each term. For a motor with voltage V equal 400 volts, rotor resistance R sub R equals 0.8 ohms, the sum of stator and rotor reactance X sub S plus X sub R equal 2 ohms, frequency F equal 50 Hz, find the slip at maximum torque and the value of that torque. First, synchronous angular speed omega sub S equals 2 times pi times 50, which is 314 radians per second. The slip at maximum torque S sub max equals R sub R divided by the square root of X squared, which is 0.8 divided by 2, giving 0.4. The maximum torque T sub max equals open parenthesis 3 times 400 squared times 0.8 close parenthesis, divided by open parenthesis 2 times 314 times 0.8 close parenthesis times the square root of open parenthesis 2 squared plus 0.8 squared close parenthesis. Approximately, students calculate. Explain how adding a 1 ohm external resistor to the rotor circuit of a wound rotor motor changes performance. The starting torque increases, the starting current decreases, and the slip at breakdown torque shifts to a larger slip value. Sketch a torque slip curve and label the 4 regions: starting, pull-up, rated, and slip loss. State typical slip values for each region.